Okay, in this video, I would like to show you how to use QAquifolium's pump tank pipe plugin to, simulate a simple pipe system. So, in order to use the pipe tank pump plugin, the first thing is that we're going to add this plugin from references, add plugin, and basically we're gonna go to where the plugin is. So you see this pipe pump tank plugin right here. So I'm gonna open that one, and as you can see, when I do it, I'll get some additional tools added to my toolbox. So I'm gonna get a tank here. I'll get a junction right there. And I'll get a pipe icon right there, and I'm gonna get a pump right here. So this is a special type of pump with a special characteristic curve. It's not exactly quadratic, even though it says, but it has a certain form that I'm going to talk about. Uh, Initially, I want to do a simple model with just two tanks connected to each other, and then we're gonna, add additional features to that. So basically, the first thing I want to model is, let's say we have two tanks and they're connected with a pipe. Um, the flow in the pipe is control in this plugin is controlled by the Hazen-Williams equation. Um, so basically, what I'm gonna do is that I will add this one tank right here. Let me just move it away a little bit, and then I'm gonna add another tank. I'm gonna move it here. So let's say this tank 2 has a lower elevation than tank 1. And then what I'm gonna do is that I will just connect the two tanks simply using a pipe. And now what I'm gonna do is that I will basically just assign the properties of the two tanks and the pipe. So what I'm gonna do is that I'm gonna assume there is a certain amount of water in the upper tank. Let's say 100 cubic meters of water, and then let's say it has an area of 50 square meters. So it has basically the water depth is going to turn out to be 2 meters, and let's say this is a elevated tank. So let's say its elevation of the bottom elevation of the tank is 10 meters. Okay, so this is the bottom elevation, and then the second tank. Let's say it has no water initially, or let's put some water in it. So let's say it has 50 cubic meters of water. The area, uh, oops, I think I did something. Okay. The area is again 50, just like the previous tank, and the bottom elevation is 0, so this is not elevated. Then what I'm gonna do is, okay, let's just give the properties of the pipe. So we have this Hazen-Williams coefficient, which has a default value of 100, and I'm not gonna touch it. The Hazen-Williams coefficient depends on the properties of the pipe, how old the pipe is, and so forth. So let's say the diameter of the pipe. I'm gonna just be conservative and pick a, I don't know, a pipe with a diameter of, let's say, 5 centimeters, which is going to be basically 0.05 meters. And let's say the length of this pipe is 50 meters. Okay, so we already built our, the simplest version of the model that we want to make. And I can just save this. Let me just save it in my document. I'm going to call this pipe example, even though I have one, which is going to be overwritten. So now we're ready. We can run the model. So let me just go to click on the run model icon right here, and this is what we're gonna get. So this is just shows what happened during the simulation. It was pretty quick. Now I can look at the flow. I can look at the flow from by right-clicking on the link, and then choosing the flow item. So this is what's happening. So we have some flow which is declining, and then it suddenly goes to zero. And I assume the reason why it goes to zero suddenly is that the water in our upper tank actually ran out. It basically finished. So let's check that. So I'm gonna go here. Let's look at the storage, and what you see is basically the water level is going down, and then it just goes to zero, and the flow stops. Now, if I want to prevent that from happening, one thing I could do is that I could just go and maybe increase my initial storage in my upper tank to, let's say, 400, even though that will mean that the initial head is going to be quite high. But I mean, this is just an example. So now if I run this, hopefully we're not going to run out of water, even though we did, but it took, oh yeah, we didn't. So the flow is decreasing because of the fact that the difference between the hydraulic head of the two tanks are decreasing. I can check that, so I can look at the hydraulic head at the upper tank, and then I can also look at the hydraulic head of the lower tank right here. And maybe if I want to compare them, I could just go and copy paste, and this is what you can see. So the hydraulic head in the upper hand is basically decreasing, while the hydraulic head in the lower hand is increasing. So now let's make the model a little more complicated maybe. So what I want to do is that, let's say I have a junction in the middle, and I want to see what the head is, and let's say the property of the pipe actually changes. Basically it's different from the property of the pipe from tank 1 to the junction is different than the properties of the pipe from the junction to tank 2. So basically I'm going to keep this pipe right here. So let's say these two pipes go in parallel. So what I'm going to do is that I will just add this junction. So now something I want to mention about these junctions is that they are sort of stiff reservoirs. So essentially there is an inherent sort of elasticity. So if the storage in the junction increases, the hydraulic head is increased, but it is increased at a kind of with a large slope, which basically forces the flow balance to be achieved relatively quickly. But I want to point that there may be the storage in the junction might slightly change during the simulation, and this was something that it makes the solver more stable. So so what I'm going to do is that I'll just add a pipe. Just by clicking on the pipe icon, I'm just going to add a pipe from the tank 1 to the junction, and then I'm going to add another pipe from the junction to tank 2, and then I'm going to indicate the properties of each of these pipes. So let's say this is a 2 centimeter diameter pipe going from tank 1 to the junction, and then we have a maybe 0.25 or 1 inch pipe going from the junction to tank 2. I have to also indicate the lengths of each of the segments. So I'm going to get, let's say this is 50 meters, and then this other one is also 50 meters. So let me save my new model, and now we can run it. So let's just run it. Went a little slower. So we ran it over a period of 1 day. So now we can look at the flows. So I can look at the flow here. So as you can see, there's a high flow at the beginning, and then it basically becomes kind of linearly decreasing. And by the way, for the junction, I can also indicate an elevation, and that can have a effect on the initial flow that we get, because that elevation is actually the initial head, indicates the initial head in the junction, which in this case was 0. So anyways, the flow in the second pipe, I can look at that, and so it takes a while for the flow in the second pipe to basically build up. I expect eventually the flow in the first pipe and the second pipe to be equal. So let's see if that's the case. I can just copy this, paste it over here, and you'll see that it takes some time for the flow to become the same, and that results in some storage in our junction. Now, if I change the elevation of the junction, it will have an impact on the initial part of the curve. So, and then of course we have we can by the way, you can also look at the hydraulic gradient at each of these pipes. So I can look at the hydraulic gradient here, for example. That is basically, it's a negative value because the hydraulic gradient is negative, of course, in the direction of the flow. But it's also the magnitude of the hydraulic gradient is essentially decreasing as we get water accumulated in our tank number 2. Okay, and then this is a flow in the original pipe that we had, the straight pipe from tank 1 to tank 2. Now, next thing, what I'm gonna do is I want to add a pump. So let's say we have a third tank right here. So, okay, so this is my third tank. I'm just gonna drag it and move it maybe here. Just make it a little smaller. And let's say this tank is at an elevation, and I want to get water from tank number 2 and pump it up there. So I'm going to leave the initial storage of this tank 0. I'm going to make the bottom area the same. Let's say 50 square meters. And the elevation of this is, let's say, 10 meters. Okay. So this is has an elevation of 10 meters. And that's pretty much all I want. Now, what I want to do is that I can do two things. I can have a pump and then a pipe, so that I can, take into account the head loss that we get in the pipe. If I want to do that, I'm going to need a junction, essentially. Because pumps are defined as connectors here. So pumps are things that connect to two reservoirs. So but now, to just keep it simple, what I'm going to do is that I will assume that we can ignore the head loss in the pipe that connects tank 2 to tank 3. I mean, you can assume that it's basically already taken into account in the characteristic curve of the pump. But we can easily, add that node too, but I'm just going to, do a simple example. So basically, what I'm going to do is that I'll use I'll just pick the pump tool, and then I'm going to connect tank 2 to tank 3 through this pump. And now what I'm going to do is that I need to provide some information about the pump. Now, if you go to there are basically there are 3 properties that we need to provide in order to specify the pump characteristic curve. The form of the characteristic curve is something like what you see here. So if I go here, or maybe if I expand this, you can see the equation is written in the description. So the head of the pump is actually equal to head 0. That's the hydraulic head if the flow is 0. Minus coefficient alpha times q to the power beta. Okay, so the beta we call it the exponent, alpha we call it the coefficient. So now what I want to do is, what I know is, because the difference between the elevation between tank 2 and tank 3 is, something around 10 meters or maybe 9 meters. The H0 has to be larger than that. So what I'm going to do is, this is the pump head at 0 flow, so that's our H0. So I'm going to go with, let's say, 15. And then for alpha, I'm going to go with a value of, let's say, 3. And then for the exponent, there's a default of 2 right there, which I'm going to keep. But if you have some data on your pump characteristic curve, you have the pump characteristic curve, you can pretty much, you should be able to fit this curve to any typical pump characteristic curve reasonably well. If not, we can simply just go to the plugin and define our own kind of model or equation for the pump characteristic curve. So I think we are all set right now. Our system is a bit more complex. It has a pump and so forth. I think we should be ready to run the model. So I'm just going to run it and hope for no surprises. So first thing, let's check to see if we have some flow here. So you can now see that we have a flow that is increasing with time. So that indicates to me that the basically water should be accumulating in this tank number 2, and the head difference between tank 2 and tank 3 is essentially decreasing, and therefore the flow rate is going up. So you can also look at the power of the pump. This is the ideal power, so as if the efficiency was 1. So this is the power of the pump, which you can multiply, basically divide by the efficiency and get the power that needs to go to the pump. So let's also check so basically what I can do is that I can look at the hydraulic head of the tank number 3. It seems that the flow rate is pretty small, so the depth is not decreasing significantly. And then we can also look at the hydraulic head of our tank number 2, which is going up much faster. This tells me that the pump that I'm using is, really not powerful enough to pump a lot of water. We can just simply go maybe and by lowering the alpha value to maybe 0.3, I will increase the flow rate. So or maybe even by increasing the H0 value. So let's just try that one. Okay, let's go here and run it, and we can see now that the depth should that's the water depth. The water depth in I mean, still our flow is kind of low, but higher than the previous condition. Anyways, this is all I have for this video, and I'll post more videos soon. Thank you.